Okie doke. So here we are, P4, factoring polynomials. We're only going to focus on two things for today. Factoring via the greatest common factor. I teach it first because you always have to try it first. And then there's a couple of shortcuts you could take with regard to special patterns. So that's what we're going to focus on today. I know a lot of you have an understanding of factoring. You think like AC grouping. We are going to do that. That's just a little later on. So if you want to go ahead and check your warm-up, there's the answers to that warm-up for you. That said, any questions about that warm-up? Comments, concerns? I guess my concern, if I'm being honest, usually what I see is some problems with this. Well, I guess another problem is that it's H and not D. Weird. The 3 really does come out as the GCF. Most students will have that. But remember, when you're identifying the greatest common factor when you have letters, you, again, are choosing how many you have in common, how many are in each thing. So when you look at this, you want to make sure that you pick the one that has the smallest exponent. So the m squared is what you should have, okay? So just check that answer, make sure it's correct. That's usually the one I see. When I grade notes, some of you are asking me about that. When I grade notes, that's a common one I see messed up. The second most common one I see goobered up is, sorry about that, is part C. Notice I have 3 terms in my answer, and you should too, right? Remember, that's a FOIL problem in disguise. So if you're looking at that like, how did I get 3 terms? Well, quite simply, if something is squared, you have to write it out twice, right? So we're actually doing 3x plus 2 times 3x plus 2, and you're foiling. So you get 9x squared plus 12x plus 4. Okay, other than that, I'm going to check and see how you guys are doing. Oh, looks very good from my purview. All right, let's get into this, kiddos. So these are your 3 methods. We're going to do GCF. We're going to do that method first. And then I have some special patterns there. There's 2 special patterns, but I actually teach them with one method. The method we're going to use on both of those patterns is your square root method for factoring. All right, we'll come back to that in a second, though. All right, first things first, zooming in on that GCF up there. All right, I teach this method first because it is the method you should always try first. It's got, I don't know, depending on how you look at it, 3 steps. Step 1 would be to, of course, identify what your greatest common factor is for all of your terms. So, do what you did in the warm-up. In step 2, you got to basically do the distributive property backwards. And then we actually always do check. You check it with your distributive property and your FOIL. Everybody good? Yeah, so GCF is what goes in that blank there. Okay, so in part A, you got 6x to the third minus 4x. 6x to the third minus 4x. Any takers on what that GCF would be there? Good, Seamus, get it. 2x. Nice. So I'm thinking that you looked at the 6 and the 4 and noticed that the greatest common factor of those was 2. They're both even. 2 is the largest number that goes into 4 and 6. And then you also just chose 1x. Make that blue. And we choose just the x because when you compare x to the third and x to the first, you have to pick the one that has the smallest exponent, right? So x to the first is what comes out. They only have 1 x in common. We wouldn't have 3 x's in common, right? All right, then this is the second phase of the problem. I open up a set of parentheses that sort of mimics the size of the original polynomial, and I'll even bring down the sign in between. And then we just ask ourselves, 2x times what gets me back to 6x to the third? And you could break that down into smaller chunks if you would like. You can start by just asking yourself, well, 2 times what gives me 6? So 2 times what gives you 6? Yes. And then you got to ask yourself, thinking back to those properties of exponents we did, x times what gets you x to the third? How many more x's do you need? I see some debating answers. Seamus. 2. Remember, we add our exponents, so 1 plus 2 gives us 3 up there. So you need 2 more x's to get back to 6x to the third. Questions on the first term? All right, we get to do it again. Woohoo! All right, so we got to ask ourselves 2x times what gives us 4x? And, you know, you could take it down baby steps, right? 2 times what gets you 4? Yes, I see some fingers. I see polite fingers, not the bad finger. That's a nice feature. Thank you very much. And then you ask yourself, how many more x's do you need? Do you need any? No. Good. We're done. The end. So that's what I mean by the distributive property backwards. See how I'm putting those arrows in, but there's like a gap? I'm going to figure that out. How do we check it? Well, we distribute. So I would ask myself, you know, and I'm going to write out what's going on in my head. You just have to do it one time. So what I'm doing is literally asking myself 2x times 3x squared. So I'm basically doing 2x times 3x squared there. And then I'm going to bring down my minus. And I'm going to distribute the 2x to the 2. So 2x times 2. And the goal in doing this would be to get the original problem back out. You know, we're always trying to produce a logically equivalent expression to what's there. So if I work out this front case right here, 2 times 3 gives me 6. So that's cool. And then x times x squared gives me x to the third. So that's a happy case there. Bring down my minus. And then 2 times 2 is 4. And I just had 1 x there. And that matches the original problem. You see that? So we're happy campers. We know that the answer to this problem is this right here. So I have my GCF factored out. Within the context of Part B, you know, you're not going to see this a ton, but this is like a hack to get through this chapter a little happier. The problem with this problem is this stupid -4 here. That's called a negative leading coefficient. When you have a leading coefficient that is negative, this factor's a lot nicer if you take out a negative GCF. So as you're looking at this, I see numbers like -4, 12, and 16. They don't all have the same x's in them, so I can't pull out an x. But so my attention is pulled to the -4, the 12, and the 16. Do you know what number they have in common?
I pulled out 4, but I guess since you want a -4.
Yes. We're going to pull out the -4, and within the context of today's lesson, it doesn't make a ton of sense, but I promise you it will make for a much happier life a little later on. So in general, when you have a negative leading coefficient, we'll just jot a note down for ourselves. Negative leading coefficient, I abbreviate that LC, means that you want to pull out a negative GCF. So let's get that negative out of there. I'm going to pull out a -4. And again, we open up a set of parentheses that matches the original size of the polynomial, in this case the trinomial, that we're attempting to factor. And then I ask myself, you know, -4 times what? Oops, sorry. So it's supposed to be a pen. -4 times what gets me back to -4 times x squared? Jesse.
X squared, but I also had a question.
Yeah, go for it.
Whenever we do, like after the factoring out the -4, do we also factor the polynomial or just leave that?
For today, you're just going to leave it. And then I'll show you how to factor the resulting trinomial. I don't know that this resulting trinomial factors, but I'll take a look. Something interesting to think about. And then I got to ask myself, -4 times what gets me back to positive 12x? So watch your signs on this one. Any takers on this part? Seamus is going to lose his arm today. Go ahead, buddy.
Negative 3x.
Yeah. I'm assuming you chose the negative there. Because, what do we got? Like negative times a negative gets you back to the positive. And then this minus 16. So I got to ask myself negative 4 times what? I'm going to cold call on some friends. I'll ask the question again now that you got the warning that I'm just going to pick a random, unsuspecting, poor student. Negative 4 times what gives us negative 16? Let me go with Professor Kashner. Ooh, very good, sir. Is that what you guys were going to say?
Yeah.
Geniuses, I say, geniuses. Yeah, you're right. Negative 4 times positive 4 gets us back to negative 16. Right now I'm entertaining Jesse's comment, like, would this factor? And I actually think it does not, because there's nothing that multiplies to positive 4 that would yield a sum of negative 3. So this one's done. Yeah, the signs are dodgy, but hey, that's not an expectation on tonight's assignment. That was just for, you know, a little preview of coming attractions. We will try to factor trinomials a little later on. Again, how do you check these things? You just distribute. So we would do negative 4 times x squared. That's negative 4x squared. That's my first term, so that works out. And then we would do, you know, negative 4 times our negative 3x. And then we would do our negative 4 times our positive 4. And then I would simplify this, right? So what I got is negative 4x squared, positive 12x, and a negative 16. And I'm pretty happy about that because it matches my original expression. So again, my final answer, however, is this right here. That is the factored version of that trinomial. Okie dokie, folks. We are 1/3 of the way done with our lesson. Pat yourself on the back. All right, actually, you could say half, because I use the exact same method on these 2 different types of problems. So what you're going to notice, this is important, we're going to use the square root method. Bedazzle this a little bit. And you're going to know to use it because check what you're going to see in each problem. In each of the problems, you're going to see perfect squares. Remember those numbers you had to list out in the warm-up? They have to be in the problem because you don't want to square root 7. Nobody wants to do that. That's miserable. You don't want to square root 3. Also, not a fun task. So we really only use this method when you can square root something cute, like 9. We could square root 9. We'd get 3. So the giveaway, or the tell, if you will, that you're going to use this second method that I'm teaching you is the fact that you're going to see perfect squares in the problem. Of course, after you take out a GCF, right? So for the first case, this is called a difference of 2 perfect squares categorically, meaning that there must be a subtraction sign in it. Sums of 2 squares actually never factor, and that's part of your conclusion for this lesson. I'll let you gnash that out in a bit. But a difference of 2 perfect squares always will have a subtraction symbol in between your 2 squares. So the form you see is sort of this perfect square minus another perfect square. And again, we're going to use the square root method to factor it. So check it out. It's actually pretty easy. From this point on, when we factor, it's like we're stuffing 2 binomials. So you're going to open up your 2 sets of parentheses for this second method today. How do you figure out what goes in them? Well, we use our square root method. So what we're going to do is we're going to take the square root of x squared. Does everybody have that written down? You got your little square root over your x squared there? And then we're going to take the square root of 4. Okay, quick question. What's the square root of x squared? Do you guys know? Go ahead, Royce.
X.
It is. Yes. So x times x gets me that x squared right there. Remember, we're just kind of unfoiling, right? So you're just, basically asking yourself, what can I multiply together that would give me x squared, and Royce hit the nail on the head. Yeah, x times x gives me x squared. Okay, same question. Now with the 4, what's the square root of 4?
2.
Yeah, Alex, is that what you're going to say?
Yeah,
She stole your thunder.
for real.
Not so real.
So, aw, you look sad. Okay, so 2 times 2 is 4. That's awesome. Yeah, square root of 4 is totally 2. All right, here's the problem. So we got 2 times 2 to get 4. But notice there's no middle term here. Oh, you got something for me, Jaden?
Yeah.
Lay it on me. What do I do?
I thought, was you about to like dive into whatever? You're supposed
Probably.
to do like a plus and minus sign, especially for this one.
Yeah, do you know why,
I
though?
mean,
Do you-
it cancels out the middle terms and leaves you with constant.
Yeah, you need that middle term to like ghost. Like you need it to go away, right? So if you think through the foiling process, what's going to allow the outers and inners to cancel? You have to have a positive and a negative for your signs. Check it out. We're going to check with FOIL, right? So we always check. I'm going to put spots on your quiz. Your quiz on factoring is like next week. But there'll be a spot to check. Why would you not check? Again, going back to your test yesterday, you all crushed that because you checked it. We would do, again, I'm foiling. For those of you who haven't done it in a while, I'm doing my first. So that's x times x. That's x squared. My outers, that's going to be x times negative 2. So that's negative 2x. My inners, trying to go with some Halloween colors here. My outers is negative 2x. My inners is positive 2x. And my lasts, negative 2 times positive 2. That's going to give us that negative 4. And then you see what happens there? Bam, bam. Just what Jaden said. The negative 2x, positive 2x, they cancel each other out. You get your original equation, or expression, I should say. X squared minus 4 was the original problem. See how they match? This x squared minus 4 matches my check, which means we did it correctly. We pat ourselves on the back. Celebrate every victory, people. Every single one. X plus 2, x minus 2 is your answer. Part B. Again, we're always looking for a greatest common factor, but 16 and 81 don't have any of those. 4, 2, 8, none of those numbers go into 81. So we just jump right into the fact that we know from our warm-up 16 and 81 are perfect squares. So we could just jump right into that square root method. So I'm going to square root the first part, square root the last part. Open up a couple sets of parentheses. And then you ask yourself, let's see who knows this one. Square root of 16x to the 4. Ooh.
4x to the second.
I heard a 4 and a, what was it again?
4x to the second.
Yeah, Jaden and Seamus, is that what you guys were going to say? Jaden, was that what you were going to say? 4x squared? I agree. Nice job. Careful though, because that's a perfect square again. So what you're going to begin to see in this one is sometimes we can factor more than one time. Oh my gosh, it's so fun. Okay, I got a square root 81. I'm thinking most of you know that's 9. Oh, do you see it?
Well,
Yeah, there's this thing in there. Oh man. 4x squared minus 9. By definition, it's a difference. And it's got 4 and 9 in it. That's a difference of 2 perfect squares. So this first set of parentheses, it's going to come down. Because the sum of perfect squares, not in our list of things that are factorable. So that's going to come down. And then I can tell you're all giving it some thought. I even hear some tapping because I'm thinking y'all are factoring this now with your friend and mine, the square root method. So you square root the first part, square root the last part. So square rooting 4x squared. That's, I'm thinking 2x and 2x. Square root of 9 is 3. And then we throw our plus and our minus. And it's done. We are happy. That is a product of prime polynomials. That's the definition of completely factored. I can't factor anymore. Alrighty. Last new one of these, and then we have our last case for the square root method. All right, part C, we got 12x squared minus 3. You're probably looking at that like, what the heck, Mrs. Lucas? Those aren't perfect squares. So now what do you do? Yeah, GCF first. I'm going to do that. 12 and 3 have 3 in common, right? Boop, boop. All right, so we got 3 times 4x squared. Gets us back to 12x squared. And then 3 times -1 gets us our 3. Ah, there it is. So we have, perfect square here. Perfect square here. So I can just do my difference of 2 perfect squares. The 3, kids are always like, what do I do with the 3? Literally nothing. Remember, we're factoring. Factors, my friends, are things in a multiplication problem. Do you see how the 3 is being multiplied by 4x squared minus 1? That 3 is now a factor. It's just part of your factored answer. It's touching multiplication. So what do you do with it? Bring it down to be part of your answer. It's a factor, right? So, and then you just have to factor the rest. So square root of 4x squared, you guys crushed this. It's 4x. Square root of 1 there, your friend and mine is 1. And then we put a plus and a minus in between. So there's actually 3 factors to this answer. And you could, FOIL and distribute like we did in Chapter P to check your answer. But I promise you it's right. We did this one right. What's up, Seamus?
When you FOIL it, that would be 16x squared, wouldn't it?
Oh, what did I do? What was my mistake? I owe you candy.
I don't know. I got the same thing. But
So I should check it. It's not right.
Yeah.
Oh, man. So embarrassing. How do I fix it? Jesse.
You did 4x plus 1 and 4x minus 1 rather than 2.
It should be 2x, yeah. I forgot to square root the 4. Good job, guys.
You did it on purpose.
I mean, yeah, totally.
Yeah, you did.
Of course I did that on purpose. I'm not recording this lesson. No, that's not happening. It was on purpose.
Because you got cheese and stuff, you have to check on it.
Yeah. Well, so it's like one of those, like, I don't point to the bulletin board very often, but there's just certain behaviors that make an effective mathematician. And one of them is that ability to, like, attend to your precision. Like, you're asking yourself, like, did I do this right? So the more I can nurture that in a student, the better the mathematician I will grow them into. So yeah, I should have checked it better. All right. On to the next. We are almost done, friends. I got 2 examples left. The method is the same, though, for perfect square trinomials. We're going to square root the first part and square root the last part, because that's where the perfect squares are chilling. I'm going to teach you that skill I referenced it earlier in today's lesson, called completing the square. It goes back to turning your left side into a perfect square trinomial. It's kind of a mouthful. For the rest of the chapter, I call perfect square trinomials PSTs. So if you want to abbreviate that when you're writing that down, it's probably helpful. But PSTs, perfect square trinomials, super prevalent in this chapter. Notice what ends up happening is we get a binomial squared. We're basically unfoiling a binomial squared. So let's take a look at what that looks like. Again, the recipe for success is the same. You square root the first part, you square root the last part. Notice I couldn't pull a GCF out of this one, because like 16 and 24 have a common factor, 24 and 9 have a common factor, but it's not common throughout all 3 things. So it's not really common at all. Again, we're stuffing two binomials. And we're going to start by unfoiling the first term. So you got to square root 16x squared. And if you're a person who wants to AC group this, I mean, heaven love you for that, but that's long. So I would take this shortcut 100% of the time. Square root is 16x squared. What you got for me, Seamus?
4x.
It is. So 4x times 4x is 16x squared. And then I got to square root the 9. That's 3. Okay, notice that when my outers and my inners come together, I get 12x for my outers, and I get 12x for my inners, right? Well, I need those to come together. Make this a little bigger again. My outers are 12x, my inners are 12x. I need those to come together to make 24x. So this is the decision you make in order to identify what symbols go in between your 4x and your 3. So what can you do with 12x and 12x to make 24x? Do we add them or do we subtract them? I think Alex knows. Royce knows.
You add them together.
You do, yeah. So because we need to make 24x that's positive, plus signs go in your parentheses. Because 12x plus 12x would give me this 24x right there. Okay, wait. The big kids don't write an answer like 4x plus 3, 4x plus 3. You would actually write this as 4x plus 3 quantity squared. All right, you are almost done, friends. It is my last example of the day. We got x squared minus 10x plus 25. Again, the method I'm teaching you to wrap up this lesson today is our square root method for factoring. Notice your last term always positive in a PST. Always, always, always. So there's a little reminder there. Again, we're stuffing our parentheses. Your square root of your x squared, to unfoil that x squared, is just x times x. Square root of 25, that's 5. If you look at your outers, that's 5x. If you look at your inners, also 5x. But this time around, they have to make negative 10x. Negative 10x. Ooh, I don't know who was first. Jaden, what goes in the first set of parentheses?
It doesn't matter if you want us to go to B.
I don't,
It's,
Rock, paper, scissors.
it's negative. It's both negative.
Is that what you were going to say, Seamus? Good job. Okay, big kids don't write it like that.
Oh, okay. Negative. X minus 5 squared.
Yeah. Quantity of x minus 5 squared. That is it. You could check these with foil. My shortcut holds some water. I promise you it does. All right. So bask in the glow of what you've done today. That's a lot of work. You now know how to factor 3 different types of polynomials, those that have a GCF. You know how to factor a difference of 2 perfect squares and a perfect square trinomial. Your assignment is that, right? So we'll go over this tomorrow. All right, so you can take a second, finish up your independent practice. Answers are going to be on your next slide. There they are, kids. Check carefully. Part B there, you had your negative 12x squared, so just keep an eye out for that. And you now know how to factor using the GCF method and the square root method. Congratulations.